what we are going to do right now is learn how a tokenizer works. So in natural language processing, you basically need to convert your natural language inputs, your normal text inputs, into more machine readable inputs. You might be reading this in compiler now in third year, or those who are in second year will study this next year. So we use something called tokenizers. It needs stuff like NumPy to generate from scratch. We're not going to do that today, but we're going to use the datasets library and the Hugging Face library to create one from a more primitive method, from more first principles. So let's begin by installing the datasets thing. You can code along if you wish, because this is going to be essentially be a code along, right? So we'll install the datasets thing first of all. Yes, and that's there. So tokenization, let's talk about it. It consists of several steps: normalization, pre-tokenization, model creation, and post-processing. So normalization is basically converting the entire set of natural language inputs into a similar set, maybe in the same language, or maybe following the same set of rules or syntax rules. Pre-tokenization is splitting the normalized input according to token rules, and the model is used to train the tokenizer, and then the post processor is used to add the special tokens, the attention mask, and type IDs. So using all of that, you can create your own tokenizer for your own given use case. You can see an example here. If you have an input which is hello, how are you today, in multiple cases, uppercase, lowercase, etc. You normalize all of that. You go to lowercase, and then you pre-tokenize the whole thing to uh, different tokens based on white space, and model is used to uh, train the whole thing based on the pre-tokenizer inputs, and then the post processor is then used to include the special tokens. So let's import the decoders, models, normalizers, pre-tokenizers, processors, trainers, and tokenizers. So we can use a BERT normalizer for any machine translation activity, or we can use base pre-tokenizers working with languages such as Hindi. We can use Unicode scripts, and we can also use byte pair encoding when we are working with byte level entropy, or something that requires an entropy instead of tokens. So let's begin this, but before that, let's load our own data set. So I've chosen a data set that's called Wikitext to raw v1. Let me just show you how it looks. So this is how it looks. This is a given document, Valkyria Chronicles the Third, and these are the given sentences, let's say, from the given document. These are the given sentences, and there are about 1.81 million rows over the course of this entire thing, right? So let's see if it's imported. It is imported. Yeah, let's go on. I'll also define a get corpus function, which will essentially be used later on while training of the model, right? So this is our starting thing. Okay. Also, of course, the tokenizer objects. So now that we have the tokenizer objects and everything ready, what we are going to do is, we are going to train a word piece tokenizer, which is used by BERT model. Gaurish was just talking about BERT models, bidirectional encoding representation trainers, and byte pair encoding, which is used as part of GPT-2 models. So this is a sample thing that I might use later on. So I just kept this here. Let's start. So the first step, anyone? What's the first step? Anyone? All right, let's just not waste that time. We are going to start with tokenizer normalization. So when we use tokenizer, we have to normalize it first. Byte pair encoding does not require this, but we will need this to be done for our BERT encoders. And we could straight up use BERT normalizer here, but then that would not be making it from the scratch. So let's do it from scratch. We'll use sequence. So where is sequence used? Sequence will be used to add all the tokens add all the normalizing layers for the tokens as required. So let's start with maybe normalizers dot NFT. What's NFT? NFT basically talks about your Unicode normalization that is done by normalizers.nfd. We can talk later about that as well. And then we use normalizers.lowercase. Lowercase basically turns everything to lowercase. And finally, we use strip accents. It's already giving me the output, generating that for me. So these three things are used to create a BERT normalizer. And let's just run this one. So yeah, it ran perfectly. Let's try using this. Tokenizer.normalize. dot normalizer dot normalize string, and let me show it to you from before. Hello, how are you? When we run that, it gives me one which is normalized according to the Unicodes, all lowercase and no accents, such as on U, O, or E, right? So we can see that it has normalized, and but byte pair encoding does not need this. Let's go on to the next part of this. So now, after normalization, we would require pre-tokenization. So how can we maybe do pre-tokenization? We can use the same thing again, dot pre-tokenizer, and here again we can use pre-tokenizers dot BERT pre-tokenizer, but let's not do that for now. Let's try to recreate that. So how does a BERT pre-tokenizer work? It basically does a few things, such as white space split and punctuation split. So if in this you can see that there's a white space between each word and there's a punctuation mark at the end of it, which is a question mark. A BERT pre-tokenizer will separate the tokens on the basis of those few things. So let's add all of this to the sequence. Pre-tokenizers dot white space split. I would want, not white space. Yeah, white space split, and pre-tokenizers dot let's say punctuation. Yes, those are the two things that I would want for my word piece pre-tokenization. And for this one, we would also need to add a pre-tokenizing layer to the BPE model. So BPE was a variable that we used. We used BPE. All right, perfect. Dot pre-tokenizer. We'll require pre-tokenizers dot byte level. So byte level tokenization is a given function Hugging Face libraries, which adds which divides your tokens according to bytes and adds a separator constant, which you will see now once we take an example. Let me also just put add prefix space as false. So what does add prefix space do? It adds a prefix space, or it adds a prefix constant. Because we have add prefix space as false, it will add a prefix constant. You will see that now. Before that, let me run this. Tokenizers, pre-tokenizer, and bp.pre-tokenizer are all done. And let me try printing a few things. Tokenizer dot pre-tokenizer dot pre-tokenized string. Hello, how are you? Should we do that? Let's go ahead with it. Let's go ahead with the same thing for BPE as well. Right. Here we'll see what the pre-tokenizers do in each case, and we'll see why each thing happens. So here you can see that the tokenizer, the first tokenizer, converts into hello 0, 5, 6, 9, 10, 13, 14, 15. These are all the ranges in which each of these tokens are divided. And if you see the second one, which is BPE, you will recognize something that's a G, which is being added because we have made add prefix space as false. If it was true, we would not have seen this. Anyways, why is this used? It is used as a separator because BPE does not have special tokens as part of its separators. But so far I've been talking about some special tokens. Let me just write down these special tokens for you. The first special token is called UNK, unknown, and then we also have a padding and CLS, which is used at the start of any segment, and it's a classification special token started at the start of it, and SEP, which is a separator, and a mask, which is used to add attention masks to a given input, text input. So now we have a pre-tokenizer, a normalized layer, and we now need to start model training for our given corpus. So we'll train it according to the corpus that we downloaded here, and using the get corpus thing, we have a data set. We'll use thousands of lines at once. So let's start with trainer is equal to let's create a trainer object for word piece trainer. So we could also create this from scratch, but this is a little verbose, so we are not doing it today. We may do that later. Vocab size, let's take 25,000, and special tokens is special tokens as we have defined before. And the BPE trainer object is basically the one used by Python encoding. Let's instead of word pair trainer, you can just do BP trainer and the same thing again. One thing for byte pair encoding is that you need not use special tokens necessarily. Like we have used it here, but instead you can also use just end of text. And we are done. We have created 2 trainer objects and we can now train. So we can train our tokenizer. Train from iterator. We have created the iterator and we'll use the get corpus. And let's just autocomplete the whole thing. Get corpus uses a data set from before. Trainer uses a trainer that we have just defined. And BP does the same thing according to its trainer. So this will take a little bit of time, maybe 20 seconds. Let's see how long it takes. So what is happening is this word piece trainer is taking the data set from before and training our tokenizer based on its rules. And so is the byte pair encoding doing it. That's it. Done. 14 seconds. We did it in 14 seconds. That's good. And I'll just get the encoding from the post processing. I'll just copy it from somewhere. Let's just copy it. I'm not going to type all that much. So in post processing, you need to have a more a way to describe how to define various tokens and how each of them are to be taken. What's the way that each of them have to be assigned, and that's why we need to use a CLS and the SAP tokens. And let's take the print the token IDs 2 and 3, and once we encode this, you will see that they are never given any weights because those are separators. We do not use them. And similarly for BPE, we will also create a post processor. A post processor is basically something that does post processing. What I'm talking about. Processors dot byte level trim offsets is equal to false. We can put that as true, and I will basically remove the G dot that we were seeing before. But let's just keep it this way. So now, even though it won't be visible, you will realize soon that this is it. We are almost done with creating our own tokenizers. Let me take an example of encoding and decoding using tokenizer. Tokenizer.encode, and I don't know. Let's put some. Can you give me 2 sentences? Anyone? And we'll put them in this and try it. Can anyone give me 2 sentences? Anyone?
I love Data Science Club.
Perfect. I love Data Science Club. Sure, that is first one. Anyone second? Any other inputs? Let's just take another sentence. Anyone? Just come up with one.
All the best or something.
All the best. Okay. Samosa for the win. Sure. All the best, and let's put samosa for the win. Yep. Okay. So those are the 3 sentences that we have. All right. And let's try printing the tokens that we have in EX, and let's also print the type IDs. So you will see that you will not get any 2 or 3s here, or I hope you do not get any 2 or 3s here. Let's see. What's this retokenized? What was this? Did we not pre-tokenize this? Let's try this. Tokenizer dot encode. What's the output of this? Tokenizer star. It's pre-tokenized. String cannot be converted to Pybool. Tokenizer dot token ID. This that. Let's try this somewhere else then. Did we miss a step before? We have trained everything. We have a word piece trainer and a BP trainer that is there. We have a train from iterator. We have trained it. 14 seconds. That's how much it should take. Maybe let's. Oh, it worked for 2. Didn't work for 3. It worked for 2. Let's see. I will come back to that error. Why I did not take 3, but it did take 2. So you can see it encoded everything. So CLS, it starts, and separators are the separators. Yeah, samosa betrayed us. I have no clue why I did, but it did. So I love Data Science Club. Into all these tokens separated, all the best separated, and you have the token IDs 0s and 1s. Maybe we'll not use samosa for the next time. And similarly for BPEX example, let's take the BP.encode and the whole thing again. Yes. Dot tokens and that type IDs. Has no underscore EX dot type IDs. Yep. So we'll try Budgie or chat or something next. All right, we will. Not. I won't have samosa next time. So this gives us, since we have trim offsets as false and the previous thing which was add prefix space as false, you can see that it does a G accented G out there, which is again, as I said, the separator. So just if you ignore that, we can see that I love data science club all the best is what it has broken down into the tokens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 tokens out here for 2 sentences. And if you decode the whole thing, tokenizer dot decoder, we create a decoding layer, and with the decoding layer, the whole thing is finally done. Once it now we can use it, and let's put this at prefix equals hash, which is a sort of again a tokenized separator. And what this decoder does, now that we have the decoder out here, we can decode anything which is in IDs. We do not use type IDs, we use ex.ids. So it will take all the IDs from I Love Data Science Club, the 10 tokens. Let's print that as well. ex.ids. Yes, those are the IDs. That's what the computer will read. And that's what it will be trained on once we use this tokenizer in a larger model. And that's the encoded part, and the decoded part will look like this. I Love Data Science Club, all the best. And that's how you do it for word piece. And let's just complete this whole thing for BPE dot decoder as well. Is design only? Oh, is it? I did not know that.
Yeah,
You
it's
learn
actually
something here.
designed for either, yeah, one or two inputs, and we have three or more. We got to either, call it separately in each cell, or, there is another function called tokenizer.encode plus. Maybe that might work.
Maybe.
Yeah,
Makes
yeah,
sense.
yeah.
And let's do it for BP dot BPEX as well, and it prints the whole thing as well. So you can see that this is the encoding decoding part, which will eventually be used by the machine to learn and extract data from your given corpus of words as well. Once you have created your own set of tokenizers, you can just import a bird tokenizer, or let's take a pre-trained tokenizer. Pre-trained tokenizer fast, and from that you can use, and for that you can add a wrapped tokenizer, which will wrap the whole thing or you can use a tokenizer or JSON, but right now we are using just this. So you can use your tokenizer object, the tokenizer, and with the given tokens, you can make the pre-trained tokenizer fast, use your created tokenizer as well. After this, you can just use it within your program, just as you use for other normal pre-trained tokenizers. Similarly for BPE from transformers, you import pre-trained. So I'm importing pre-trained tokenizer fast because I've used it. You can import it for this as well. Wrapped BPE equals pre-trained tokenizer fast, and tokenizer object equals BPE. And eventually, actually, you can just make this run as well. You don't need any of the tokens there. Once this is done, you can straight up use it in any of the programs that maybe even Kaurish told us about, or in any of your NLP projects. Maybe you can use byte pair encoding as a measure of entropy for more non-English family languages, something that uses more Unicode characters and stuff like that. So that's there, and you have created your own tokenizer. Thank you so much.
Thank you, Shourya. It was a very well structured workshop for the, creating our own tokenizers.